Welcome to the recording of section 3D. In this section, we're going to basically focus on two topics. The first topic is to define a linear map is invertible. We're going to explain that idea. And then after we give the definition and give an example, then we're going to talk about when a linear map is invertible, that is equivalent to that linear map is injective and surjective. Recall that injective means different inputs goes to different outputs, and the surjective means everything. If you have a map from V to W, every element in the W, you can find at least one V corresponding to that W, right? So then we're going to show these two conditions together, equivalent to the map is injective, is invertible. And then, so that's probably what we're going to do in this recording. And then in the next recording, we're trying to look at using the definition of invertible map. We're going to derive a new concept called two vector spaces. They are isomorphic. So in other words, they almost the same. It's just that they have different names for the elements, but in terms of the structure, there's not any difference. And then from there, we're going to use that to also study the dimensions of some vector spaces, because if we can establish this kind of isomorphic vector spaces, then some ones we know really well can be used to study some ones which are relatively newer for us. All right, so that's the whole idea of this section 3D. So let's get started to first introduce the definition of let's first introduce the definition of the invertible linear maps. All right, so here's our first definition here. So a linear map T belonging to this vector space containing all the linear maps from V to W, this T is called invertible if there exists a linear map S, which is belonging to the L from W to V. So basically, when the T take from V to W, the inverse, or of course right now we call this S, eventually it's just the inverse of T, will take something from W back to V, right? So this is the same idea as the inverse functions you have seen in earlier class. All right, so S will take the it's still linear map, but take W to V such that there are two things. So the S times T, remember this also means the composition here, right? So if T take a V to W and then W take and then S take a W back to V, so then this composition as T is from V to V. So this equals the identity map on V, and the TS. All right, so remember S take the W to V, and then the outer linear map T will take that V back to W. So this is from W to W. All right, so this equals the identity map on W. All right, so a linear map S, which belonging to the same LW are satisfying ST equals I and TS equals I. This is called an inverse of T. inverse of t. All right. So these two capital letter I, they are not the same identity function. All right, because ST is from the vector space V to the vector space V. So this first I here is the identity defined on the V space. And the TS is mapping any W element to the W vector space. So it's from W to W. So this second identity here is identity defined on the vector space W. So they're not the same I there, or even though we just put a single letter there, but do not get confused. And let's make a quick remark here. I think the neural addition probably call it a proposition, but what we're trying to say is this inverse is unique. If there is an inverse, right, then this inverse of the original linear map T is unique. All right, so let's quickly prove this, or this idea had been happening at the very beginning of the semester, or it's a similar idea. So let's assume if there are two inverse S and S prime are both inverse of a linear map T, then how do we show they are equal to each other? We want to show they're equal to each other, therefore it's unique, right? So then that means the S is, we can write the S as S times an identity function, because the composition between a linear map and a properly defined identity function is the same as the original map. And then once we have the I, we can write this I as the T times S prime. This is also the identity, right? So T times S prime. And be a little careful here, right? So really, even though we put this just as the pretty straightforward proof here, but you really need to think about like what the vector space is all those maps are talking about defined over with. All right, like the S is from the W to V, so that's okay. And so that the second term on the in this expression here, in this sequence of equations here, the S times I, right? So where that I is from, right? If you think about this, is well, the S is from W to V, so that identity function on the right hand side of S, this must from V to V, all right? And this trying to look at, this one is must from W to W, right? So you can send the W to W and then S take something from W to V, right? So this I is from the W to W, right? And then when you look at this, we're saying, well, this is same as a T composed with S prime, right? So does that make sense? Well, if the S prime also takes, if you think about this, is if you begin with the W S prime, that take the W to V, and the T is taken from V to W. So that tells you that the TS prime also take a W to W, so that's okay, right? So this, all the vector spaces are in the same order, so we're good. And then we can associate, we actually already proved that when we talk about linear maps, we have this associative law here. You can associate in the terms of the product, you can associate any way you want. So then this is the S times T and then S prime. And then, but we know, since if we know the S and T, they're inverse of each other, then S times T is also the identity, right? And then times S prime, right? So the S prime, the same as S, is from the W to V, right? So this identity here must from the V to V, because we begin with a vector in W, S prime take W to V, and then this I will take the V to V here. And then at the end, this composition is also equal to the S prime. All right. So therefore, All right, so the inverse, all right, if t, maybe let's say, all right, if t in the LVW has an inverse, then the inverse of t is unique. All right, so if there's one, then there's only one by the definition and by this proposition. All right, so we know that's unique. Now, once we know this is unique, then we can give it a notation, right? Because we do not have to worry about, well, what if there's two or three, right? One notation is enough, is not enough to cover, different ones. But if there's only one, then we use this notation, all right? So, so the inverse of t, all right, so where is denoted by the t, and we put a -1 in the upper right corner. Right? That's not a 1 over t. That just means the inverse of t. Right? So let's look at a very simple example here. For instance, if we have the t from NA Fn to Fn, right? Either the Rn or Cn, doesn't matter. And then this is defined by, let's just make a scalar multiplication. Maybe t of Na x in Fn is just 1/3 times x, right? Then it's pretty clear the inverse of t will be 3 times x, right? So this is the inverse. And then how we know this actually is indeed the inverse, then we can check the t times t inverse of x. This is 1/3 times 3x is equal to x. So this is the identity, right? And then the t inverse times t of x, then this is 3 times 1/3 of x, which is x. So this is also the identity, all right? So then this tells you this t inverse is indeed the inverse of t, or maybe I should use s there. But this gives an example, like a very basic example, but this tells us, yes, we have the inverse, right? And I guess another thing to explain this is, why we care about the inverse, right? That's probably can be seen from like your linear algebra class or some other classes, right? Because a lot of times when we're trying to solve for equations, like at the very beginning, you even in the probably for the students in the middle school, right? When they solve the like a linear equation, something like 5x is equal to 7, right? So then the two ways to look at this is, well, we can say, well, we divided by 5, right? So then, well, if you divide by 5, you get x is equal to 7 over 5. But the other way to look at this is, well, 5 is a number which has a multiplicative inverse. So if you multiply by the inverse of 5 on both sides, so then that tells you the x is 7 over 5. Okay. And then similarly for a matrix equation, if you have a square matrix A times x is equal to B, right? If this square matrix has an inverse, then that's good because we can apply the inverse from the left-hand side to both equations, multiply the A inverse from the left-hand side, and then the A times A inverse is the identity. So then you have the identity times x is A inverse B. So this implies the solution of that system of linear equations or the matrix equation is the A inverse times B, right? So knowing a linear map has an inverse, that's going to be very helpful for us if we want to understand how you go back from the W to the V there, right? So that's really useful. And of course, the other application of the inverse, as we will see in the next recording, is, well, if you have an inverse function between the two map between the two vector spaces, well, then that tells us these two things are almost the same. All right. So then that's another very nice way to interpret the significance of the inverse maps. So let's prove another property, all right, before we move on to talk about the applications. So let's look at, I think this is 356, the proposition. This one claims a linear map is invertible, if and only if it is injective and surjective. So again, many times we have seen so far is if we have a if and only if statement, or that's nice. That's equivalence conditions. You can either use the condition on the left hand side before the if and only if, or after if and only if, right? So it depends on which way you want to go. And we really need to construct two proofs here, right? You assume one way and then prove the other way, and then vice versa. So let's probably just begin by assuming the map is invertible. But remember, this must be a linear map. So we are going to assume that T is in the LV to W and the T is invertible. It's invertible. Then what we need to show is, then we want to show two things. We want to show T is injective and T is surjective. So I want to do two things. And then let's recall, right, what do we mean T is, how do we show that T is a linear map is injective, right? So we're going to begin by saying, well, what if T of, let's say, V1 is equal to T of V sub 2, right? Then the same output implies the input is the same, then you can from there show the T of V1 is equal to T of V2, show the V1 equal to V2, then we're done, right? That means the T is injective. So assume T of V1 is equal to T of V2, right? Well, since T is invertible, so we will apply the inverse of T to both sides of the equation. Then we have the inverse here is the inverse of this, but we know the T inverse and the T will give us the identity. That's the definition of when T has the inverse. Then when you multiply T and the T inverse, no matter from which direction, you always get identity in the either in the V or in the W, so in this case in the V, and then that implies the V1 is equal to V2. So this tells us the T is injective. Very nice. And then the next thing is to show T is surjective, right? So what we mean something is surjective? That means every element in W, you can find at least one V corresponding to that W under that map T there, right? So then for any W in the vector space W, so we're going to take a V equals the T inverse of W. And then this is well defined because the T has the inverse, and the inverse actually take the W back to somewhere in T in the vector space V there, right? So this is a T inverse of W is a vector in the vector space V there. All right, then let's look at what is the T applied on this V there. So T of V is equal to T of T inverse W, and which, again, we use the same property is this is identity when you multiply the T and the T inverse, so we end up with W, right? So that tells you for any W, we are able to find a V corresponding to this W, then that tells us the T is surjective. All right. I think this direction is pretty, naturally just follow the definition of the T is inverse, invertible, then we can easily prove both properties we hope to prove is T is injective and then surjective. So now let's prove the other direction. We're going to assume T is injective and surjective, and we want to show T is invertible. Well, that means, so we still have to follow the definition, right? So far, the only thing we can use to prove the T is invertible is the definition. We do not have any other things we can interpret outside that definition. All right, then how do you show something is invertible? In other words, we need to show there, by the definition means we need to show there exists S which is linear from W to V such that the ST and the TS both equal to an identity function in the appropriate vector space. All right. So then there are three things we need to verify. All right. Well, actually, yes, three things we need to verify, but we need to first actually find what this S is, right? And then after that, then the three things we need to verify is S is linear from W to V. All right, that's important, right? Because by our definition, we want this inverse also to be a linear map. All right, so that is sometimes it's pretty clear according to the context. Sometimes we, in this kind of proof, we at least you need to mention that, or in this case, actually, we're going to strictly prove that. And then you also want to prove the TS is the identity, ST is the identity. Are they not the same identity function as we have emphasized? All right, so you still have to check each of them separately, right? The TS equal to identity does not automatically guarantee the ST is also the identity function, or vice versa. So we do really have to check all the three things. So let's think about how do we construct the S. All right. And well, remember the condition you can use is this T is injective and surjective, right? So I will draw a picture here. Let's think about this, right? So first, the T, this is V, this is W here. So the T is go from here to here, from the V to W. And then, so your S, no matter how you define that, first, it must take something from W and then back to T. So back to V, right? So the S must go from somewhere here to take any element W back to something else, right? So of course, here's if there's an element of V there, the T will take it to the T of V. And the W, how do you do that? Well, but remember, what we want is the composition is the identity, right? And so for any W here, first, we had to ask, can we find a pre-image, or can we find something, the T of that V give you this W? Well, the answer is yes. We're at least able to find such a V, because remember the T is surjective, right? So if you put a W here, then you're always able to track back to find the V such that T of V equals to W. And then, of course, if there are more than one, then we probably end up in trouble. But the T is also injective, right? You cannot have two different V give you the same W. So that means when you go backward to track that pre-image, you only can find one. You are able to find one, and you will only be able to find one. All right. So then this kind of fashion will define the, well, at least right now it's a map we want. All right, so for any, so what we are saying is for any, let's write this down here. So for any W in W, all right, so we define, so this is our like artificial definition here, right? So we define SW to be an element, I'll put a V here in V, such that the T of V is equal to W. In other words, this definition will take a W back to the V there, and we actually define this map by a description, by saying, well, what that V you look for on the other side, on your original V vector space there. Well, the way we look at that is there is a V, T of V will be equal to that W, and there's only such a way, T of V equal to W. So now if you with W, you go back to say, well, that's the way I want, and then this will take any W to a vector in the V space. All right. So then there's three things, and all right. So the existence and the uniqueness of the T, or probably we just say since T is surjective, so that's guarantee the existence of the W, then there exists such a V, right, for any W, right, and then since T is injective, then this such a V is unique. It's unique. All right. So therefore, this definition is well defined. All right. So this is a meaningful definition here. And then what now? So we kind of at least described what S is by this definition. Then the next thing we need to check is, well, the composition, or the, if you want, the product or the multiplication between the T and S, or S and the T equal to the identity. And then we still have to check the S is linear. The order does not matter. You just have to check all the three things. So let's first probably verify the T. So by the definition of S, we know the T of SW is always equal to W, right? Because how do you define what is SW, right? If you look at it here, right? So our SW is a V, right? And the T of that V, this, remember this V is the same as SW there, is T of this V is equal to W. So that's by the definition, this is always true for any W in the W space. So then the TS, this tells us the TS is the identity, right? So on the vector space W here. All right. And then, so next, we want to show the ST of V is always equal to V for any V in the vector space V there. Because if we can do this, then this tells us the ST is also identity on the vector space V. So do we have this one? Well, let's start with the trick here, saying let's consider the T of ST V. So we first add a T here, and then let's see how this is going to help us. And then we can associate those three maps ST, TST, right? The product any way we want. So let's put the TS together, and then let's put the TV together. And the TS, well, we already argued just a few seconds ago, the TS is the identity. So then this is the identity times T of V. Well, but the identity applied on anything is that element itself. So then this is the T of V here, right? Well, what this tells us is or look at what we're trying to prove. We're trying to prove ST applied on V is still V, right? So right now we have, well, it seems that we make things a little bit more complicated. We even throw in an additional map in front of your equation, and then, but keep in mind, we already know the T is injective and also surjective. In this case, since T is injective, then if you have T of something, actually this is T of STV is equal to, you look at the end, or let's ignore the intermediate step for a second, you're saying T of this bunch of thing on the left-hand side is equal to the T of V there. So then this tells you the STV, which is the input of T on the left-hand side, is equal to V, which is the input of the same T on the right-hand side. So they equal to each other, and then this is for NAV. Right? So that's what we want to prove. So that tells you the ST is also equal to the identity on the V space. Okay, so this is three things we need to check, and we checked two, right? We checked the TS and ST, they are both identity functions on the corresponding vector spaces. So then the only thing we need to left to do is, finally, we still need to prove, almost there, but we still need to prove this S, which is right now it's at least a map from the W to V, is linear. It's linear. All right. So how do we show something is linear? All right. So in other words, we want to show, right, for any, so two things you need to show, right? For any W1 and W2 in the W, S of W1, W2 is equal to S of W1 plus the S of W2. All right. I think sometimes I use parentheses, sometimes I do not use parentheses, or it's the same meaning. Yeah, I guess I probably already get used to put the parentheses there, but the book most of the time I do not use that. So, but the same thing. All right. And then secondly, we want to show for any maybe scalar A in F and a W in the vector space W, we have SAW is equal to ASW. Right, so I probably prove one of them, left another one as exercise or a similar idea. Right, so this is really, we still have to somehow, you still have to think about what is the definition of W, and then secondly is of S, and then secondly, well, since S is defined using a way or kind of indirect way associated with T, so then you still have to consider using the T somewhere in your proof, right? So let's focus on the first one, or second one is exactly the same idea, is, well, what do we mean S of W1 plus W2? All right, let's look at the left-hand side, right? Well, remember the S of W, let me scroll back for a second here, right? So how do you define SW, right? SW is a vector in V, right? And that V is not an arbitrary vector in the vector space V. We choose that V because the T of V equal to W. So that's how we establish this correspondence from a vector W to a vector V there. So now if we are trying to prove this S of W1 plus W2, right? So what is the meaning of that? So that is a vector in the V such that the S of that V, T of that V is equal to W1 plus W2. That is the meaning of this S of the sum, W1 plus W2, right? Actually, I'm put here, S W1 plus W2, right? So this is a vector V in the V such that T of V is equal to S equal to W1 plus W2. All right. So this is by our definition of S. So that's how we interpret this notation here. And so let's look at what is T of S W1 plus SW2. Right? Remember the SW1 is in V. SW2 is in V, and V is closed under addition, so the sum is still in V, right? So T of this, well, T is linear. So that allow you to distribute the T to both terms in the sum. And then this is the TS W1 and the TS W2. However, we already proved the TS is I, right? That's, when we check the three things, this is the first thing, or second thing. This first thing we checked, right, is here. Right? TS is equal to I here. So we have that. And then, so this is I times W1, and I applied on W2. So this is W1 plus W2, right? Well, then that is exactly something we're looking for, right? Because we said, what is the SW1, W2? That is a V such that the T of that element is equal to the sum of the two W vectors. But we look at the T of this SW1 then plus another quantity SW2, we found, well, this actually give you the W1 plus W2. So by the definition of S, then this, we have the S of this is S of W1 plus S of W2. All right. So then let me make it clear. So the proof of SAW equal to ASW. All right. So let's left this as an exercise. All right. For the definition, it's a similar argument, right? So if we have all this, then we proved this proposition, I think 3.56. So the argument on this page is focused on the other direction. If you assume a T is injective and surjective, then we're trying to prove then the T is invertible, right? And the invertible means there exists such a linear map S, or STTS, are both identities. So we prove that. I think that's the natural place we can conclude the first recording here. All right. So to summarize, we introduced the definition, what means T is invertible, and then this invertibility we're going to see the use in the next recording, and then we proved the proposition. All right. So next recording, we're going to use this invertibility to define the isomorphism, and then we're going to go on from there to develop some more interesting properties. All right. See you in the next recording.